So, hello everyone. Good morning. I think now is a good time to start. Uh, I don't know if you have noticed that we uploaded this term project. It was for the last semester, and here it's a full report. What exactly are we doing here? It's exactly the same. So. And the report is supplied with many screenshots, so you can see from step 0 anything you need. So here where we enter components which are not defined in the software, and we go through the steps as we usually do here in the lecture. So starting from entering the composition, trying to match the oil density as at standard condition, and showing the saturation pressure. And this is maybe additional step, but you will take that in next lectures. So, and here how we do grouping. It's something important maybe we will need in the term project. And here how we enter the saturation pressure, and how can we match that, and so on. So it's exactly the same. It's explained step by step with screenshots. So anyone who faces any problem should read this report, at least until this point where today we will start to deal with DLE. So you found this. You will find this report in StudIB. Okay. Yeah. For today, we will try to match DLE. And before I start working on this project, I prefer to make a review for what we have done so far. So, in previous lectures, you remember that we always draw this, which is PV plot. And when you deal with and before this also we can show the phase envelope or phase diagram. So here this is the critical point, and if your reservoir condition in this side, then you have oil. If you are in this side, then you have gas. And we have different types of gas. Sometimes your gas is starting to condensate inside the reservoir. And here the separator condition. So this type is called gas condensate. Sometimes your gas does not make any condensate inside reservoir condition, but at the surface you will find some condensation. So this is wet gas, which is always dry inside the reservoir, but in the separator you will have, it's not necessary to be exactly here, maybe it's here, but just to make it simple. If you have, so this is dry gas. This is gas condensate. Okay, wait. Sorry. Wait. So dry gas is always out of the two-phase diagram. This is dry gas. Theoretically, you can model this gas only by PVT. PV equal to Z RT. this gas, wet gas, from this point to here, you can model that by this equation also. But this equation has one problem. Z factor, you need to find the suitable Z value at each condition. So it's not or helpful to use it inside reservoir simulation as a model. However, this part here, or this part here until this point, or this part here, is exactly this part. Once you enter here, so once you enter here, you enter two-phase region, which is the same here. And this region, for this region, you need either, if you have gas condensate, you need CVD. To know the behavior of two phases here, you need CVD. And we take this in the course. So CVD is about describing the gas condensate at two-phase region. Now let's move on with oil. Oil, it's simple. From here to here, you have only liquid, and in the reservoir, maybe you produce until you reach bubble point pressure, so you will have some gas. And this oil will shrink until certain point. At that point, you may not have a lot of liquid. You will lose some liquid. That liquid will vaporize. So to describe this here, for oils, we need DLE. However, CCE, constant composition expansion, it's used to describe this part here, either for oil or gas. Is that clear? So, if we are above the saturation pressure, if oil, we are above bubble point pressure. If gas, we are above dew point pressure. This stage, where we are above saturation pressure, we can describe this by CCE experiment. So that's why, if you see, maybe it's better to show it here. So that's why, if we show this slide, you see that we have the CCE here, just to make sure, it's for gas condensate. If we have only gas, we don't need to do any measurement, because you can describe that by PVTs and other. So CCE, dry gas, there's no tests. You need just gas chromatograph to know the composition. If you know the composition and gas gravity, you can apply this equation and know the behavior of that gas. So we are talking now if we have gas condensate and oils, which tests should I use? So if you have oils, you you need differential regression, DLE. But if you have gas condensate, you need CVD. This is below saturation pressure. But if you are above saturation pressure, then you use CCE. Is that clear? So our exercise today is now about DLE. Before, we said that when you do tuning process, you go through steps. So you have step 1, 2, 3, 4. At step 1, you enter the composition and you try to match saturation pressure. This is step 1. Step 2, you try to match BSAT and CCE. So you try now, this one is matched, but you will try to match CCE with keeping your saturation pressure matched. So it's not useful to match CCE and then you mismatch the value here in the saturation pressure. Usually, in this step, when you match your saturation pressure, you will find that there's no big error here. Because if you deal with liquid and you use volume shift in this stage, this curve is always like this, but whether it's here or here, then when you shift this curve to the exact point, you find that your CCE experiment is matched already. When you match this point using volume shift, as we have seen this. So now you will have a problem here in this part. And this is DLE today. So now we will try to, we are in this stage 3. We will try to match DLE, and we should also keep our saturation pressure and CCE data matched. That means you need to calculate average absolute error after each tuning process to see have you improved it or not. We mentioned before that when we deal with the equation of state, we should not force our equation of state to match the data in a wrong way. So, because for each property, you will need to use the suitable parameter. For example, we use volume shift to improve density. And today we will see, we use critical volume to improve viscosity. You cannot use any other parameter to improve viscosity. You only have critical volume. So, and you don't need to memorize that. It's all of them, those notes are written here in the procedure. But the main idea or the main notes that you need to remember are written here. Here it says, we usually use the pseudo-component properties to improve our results. And we use PC and the centric factor as a tuning parameter. This is general rule for most of, properties that you need to improve. However, for density, you have a volume shift. For viscosity, you have a critical volume. This is general rule. It always works, except for some properties that you need to use other properties. However, these properties are adjusted within a small range. Why? Because equation of state is built according to physical facts. So it should not be so far from the real results. So that's why there's a rule to edit those parameters inside a small range. And what does it mean, 0.9 and 1.1? It means for those properties, I will change them either 10% plus or minus. So that's it. It means that I increase critical, for example, this value, TC, I increase this value by 10%. So I have a range. I should not avoid that range. However, if you have difficulties to match your data, you are allowed to go even up to this range, but not more. Usually, it's not more than 1.5 or less than half. But be careful. At that range, you may open a big door for you, where you will be in trouble with your equation state model. So it's danger to go in a big range. So here, today, we will start by defining the differential regression experiment. How we define that, we have seen this. When we have experiment data, we just open the, I will need to open the software. So when we want to define an experiment, we just came to this icon. By the way, it's the same icon in PVTI. They always show this. It means enter your lab data. So here, in this window, we enter saturation pressure, CCE, CVT, and differential liberation, and any experiment data we have. This data is my reference form. It's not usually, equation of state is not usually able to reduce the same of this data, but we tune our equation of state to match this data. So this is my reference data. And okay. So in the first lecture, we have entered the composition, and after entering the composition, we take the saturation pressure, we enter the saturation pressure, and we match at this point. And now, someone may ask, at this point, after matching saturation pressure and CCE data, this one, how I can know is my equation of state is accurate or not? So if we are going to draw the same, so if we are talking here, so from here, now we are talking about oil. From here to here, this is CCE. This point, bubble point pressure. So here we usually don't have big problem. But you cannot, from this until this point, which is step 4 in our step 2 in our which is here, You cannot know from this step whether your equation of state is good or not. When you see that in this step and in this step. So am I, the question now in this step, am I able to reduce all these experiments within average absolute error less than 5%? If you are less than 5% and you need to stay also here with all same experiment in addition to separator test, you stay also here below 5%. So the question here, am I able to stay below this value or not? If yes, then your model is okay. If not, then you may need to improve this model. And if you could not achieve this value, it may means for you to go back from this step and try from step 1 again with splitting the pseudo-component to, for example, to 4 instead of 3. You try another thing. So today we will see how to deal with this part. Because only doing only this, it can be your first figure until this point has several cases. It may be like this. It might be like this. So which one is correct? The one which is correct, you will see it through DLE. Because from here you will match the percent of liquid and gas. Then those lines will need to have the correct space entry. Yeah. Those experiments. Yeah. You have. We will see this now. Each time we do a tuning process, we will take the results, compare them with CEE or CCE and DLE, then we see the average absolute error. From this value we know, and we will do that today. So define a differential liberation expansion experiment in the equation of state software. So this is the first step. I take the model for the last lecture. So our first step today is the last step, last lecture. So I don't know. This is the model which was used for last lecture. Maybe I instead of saying that we match oil density at standard conditions, saturation pressure, and oil density at saturation pressure, maybe I call this, for example, CCE. Now I will copy the same one and I will name it DLE. Then I will build that model. Do you have a question?
Are you recording our?
Yeah. So I just take this, copy it, and name it DLE. So now it's exactly the same, but we will enter DLE measurement here, and we will try to improve or match DLE data with keeping the saturation pressure and CCE match. So how we enter that? If you remember, we already have an exercise which contains the lab measurement for DLE. So now I have a pressure, I have a RS, beta O, oil density, and oil viscosity. So temperature is 220. Watch out here, maybe you have the same, in my case, the density with pound per cubic feet. But in your data, the density is not with this unit. So you can enter OK before entering, you need to cancel to go out from here. You can save this by saying OK and go back to units, and then you go to density where you choose it to gram per cubic centimeter. And it's better to do that also for output. Why? Because we will run our equation of state. We will take the output and compare it with the lab measurement, which is always in this unit. And at the end, we will be able to calculate average absolute error. It's not, logic to compare or to calculate average absolute error when you have a different units. So say OK, and then we go back here, differential, and we found that it's OK now. We can talk about weights from now, or we can keep this until we start doing the tuning. Because now just we enter into weights in this point. It's not needed, but you can do. You can enter the weights because, as we already said, that we need low weights for volume and medium weight for density, and viscosity is always matched alone, so we don't need weights here. So we say, OK. And now we enter lab data. We will try to use our equation of state models to reduce the set of this data, and then we will compare through the average absolute error this data together. So we are talking about solution gas oil ratio, relative oil volume, which is formation volume factor for differential liberation. So sometimes it's called relative oil volume, and sometimes it's called formation volume factor with VFD for differential, because it's different from what we use in reservoir engineering calculation. That value here, it needs to be fixed. You already heard about that with process gas. At the end or late time of this training, you will know how to do that. But now it's not the time to talk about it. So we match GORD, beta O D, oil density, oil viscosity, and Z factor. How we see those results for the equation of state? We will need to take the same of this pressure here stages, go with them with differential. I said to you before, all these bottoms from here to here, it's about predicting the properties of your fluid using equation of state. So this is simulation by equation of state. Here you enter real data. Here you simulate experiment based on your equation of state. So now, or today, we will try to simulate differential liberation experiment. Before we do PSAT, we did PSAT, we did CCE. Now we don't have gas condensate to do CVD, and we go to differential. So we need to enter the temperature, and we choose from here. We will do this for this model. We will enter the so when we press calc, and again, so now using our equation of state model, we could reduce all properties according to these conditions, which is pressure stages that was already used to describe differential liberation experiment. So now we can, by this function where we plot different data, we can use that to show how will our equation of state is able to reduce that experiment. So from this, you found that your equation of state, reducing this one, but your lab results are here. So there's error. It should be, matched with this. Be familiar with this because this is used in a lot of, studies, also in reservoir simulation. When we do history matching, we take data, read data measurement, for example, oil rate or water rate, and then we put points. But for the mathematical model or simulation model, we do that as line. And we know that that line should always be above those points. It means that here, in this case, our equation of state model needs to be improved. But this is for gas-oil ratio. Let's see how our equation of state model is able to produce beta O for differential liberation experiment. So just choose that from here, and you found that it's okay regarding to beta O. Let's see that oil viscosity. So the model is okay. We have oil viscosity and we still have oil density. So and you remember that we already matched all this. So all of them are okay except gas-oil ratio. So we have a problem with this one here. So, and I can say that from this point or at this point, when you try to match this one, you will mismatch the other products or the other measure. So your duty now will be how can I match this to here without destroying what we have so far. We have all data matching, but unless except this one. But it's not easy. In this step, it's not easy to make this match it with keep that experiment match. So, but here in the software, you cannot say how much it would be very nice if this absolute average error is is shown here. But we need to calculate that by Excel. We will do that. So now we are in step B. We will try to take the results for solution gas, oil ratio, relative oil volume, and all of those to compare them with lab measurement. So in this Excel sheet, I will name this lab, and I will take the same here, and I will name this equation of state. So how to take these values? It's easy, just from here. From here, you take, for example, gas oil ratio. So now we have lab data and equation of state. So now we are able to calculate average absolute error. And I will do that here. So now you need to do this just for the first one, because for those you can do it like this. And so here it's not important. So this is the absolute error that we have. We found that this one is already matched, so we have a low average absolute error. This one it was low. This one was in the middle, and this one was very bad. So this is not accepted. All of this can be acceptable, except this. You need to stay below 5%. I mean, we wish to stay even below 3%. But if you could not solve that, maybe it depends on you in the case for which purpose do you need that model. But in general, 5% can be accepted. So now, what we will do, we will try to improve our model and take those values again to compare them here. You will see that In
There's a function in Excel to calculate the average exposure.
we to me I just
Yeah, you apply that function.
absolute, and then here I said average. Average. You will find that in our procedure we said that we need to do it, this only also for Z factor. So maybe you try that at home if you wish. Just add Z factor here from lab measurement and take that from your equation of state model, and Z factor can be here. We can do that now, but just it's usually done for as indicator. It's, I mean, if your model is okay, this value should be okay. Maybe we add this here. So so it's just take this from, we have Z factor here with data, and maybe you include that with this Excel sheet. To me, oh. So you see that we have a low percent here also from Z factor. So now we finished step B, and this is important point. Try to minimize the absolute average error below 5% by matching the DLE experiment, considering the fact that the results from the previous projects, PSAT and CCE, should not get a lot worse. And before starting doing this, we need to read those notes. So the first note, do not forget to assign the suitable weights before regression. So we have weights, we should assign that to each problem. So we use, as recommended, we use medium weighting factor, which is 20. In PVTP, it's 5. This is in textbooks, and this is in PVT. In this software, they changed the way of giving weights. And this is for oil density. For GOR and beta O, D, for differential, we use low weighting factor from 1 to 3. Why we use from 1 to 3? And in PVT books or textbooks, you will find they say weight should be, always in this range for volume, and it's used for GOR differential and beta O differential because they are just a volume. Here we divide the volume of gas and volume of oil, and here we divide volume of oil at different conditions. So we have volumes here. So that's why we use this way. The second note here, oil density can match it in two ways. you can either do that in a separated way. So I try to match my saturation pressure, my CCE data, and DLE data without including density from CCE or DLE, because we have two densities now. We have density from CCE. You remember here, if we show, by the way, if you press close, you may need to enter the pressure stages again. But just do main, to go to main menu. You remember in this step, when we matched saturation pressure data, we matched the pressure and the density. So we are talking about this density. And we have another density in differential now. This one, oil density. What's the oil density when I lose gas? It should be increased. The oil will be heavy. So this density and this density, when we go to the tuning, we can exclude that from here. The question now, do I need to match the density in one step with other experiment, or do I need to check all these experiment here like this, or I exclude oil density, and after matching all of those, then I repeat matching those. Both ways are accepted. You can do both. However, you will take the way which improves your results. This is regarding to density. For viscosity, you always do it separately. And in this software, they were smart enough to separate it in different sites. When you press this, all of those will be unchecked. But when you go back here, it will be unchecked from here. So you cannot match this with those or those with this. But in other softwares, you might not find this. Here it's okay, it's good to avoid mistakes by people who don't have the suitable background to deal with this software. So here it's okay. I think in PVTI we don't have this. In other software you don't have this. So you need to remember these things. So now I will start by giving weights for those, and then I wish that everyone start tuning process. But before that, don't forget to give weights. So we already give weights for density here in saturation pressure. We give 5. For CCE we give 2 because it's volume. For differential, you need to give those are also volumes. You can give 1 or 2 or 3. So maybe we start with 2. When you press set weighting, you will find that the color is changed to blue. It means that this property has different weight. It's not 10 because all of them, the default is 10. All of them has 10. So now we do the same for beta. Oh, we give weight. For density, we give 5. By the way, 5, it means nothing when I match density by itself. When I match one property, weights mean nothing because we don't have other values to give different weights. But when you match density with different measurements, for example, oil formation volume factor, then weight will play big role. They will focus here because here. They will focus here on density because here the weight is 5 and here is 2. There is another thing here, which can be important for you. You may exclude some points from tuning process. How you do that? Just here match point. It means that the software will try to match all of those. But you can exclude some points. So I don't want to match this and this, this and this. Sometimes, or someone can ask why. Why I exclude some pointers from matching. So that's clear from here. If we are talking about GOR, which always looking at like this. So someone may say to me, I don't need to match this point and this point and this point and this point until here. Because I know if I match just this point, this is constant for me. So the software just will be confused in this range. Because you will give weight for all these pointers, and the software will try to change properties to match these pointers, which can be excluded. Just ignore them. Take this point. If you are talking here, yeah, that may be correct because this curve may be like this or this. I don't know. It's not clear. But here it's constant. So take that as a rule of thumb. The most important point that you think to match is always this point here. In DLE, we don't enter these points. We don't deal with this part. I mean, you say you already saw that last week, our last lecture with Professor Ganser, that Schlumberger, or in the report which was given, they give in DLE, they give points here. If you enter that points in DLE and you want to match that points, you may destroy your equation of state mode. So just always take this part like this. And if you ignore all points here and just play with this point, it can be useful. Because if you take this point, if you deal with single, the general rule is always saying like this. The less points that you deal with, the easier it will be for you. So less points, easier the tuning process. It means maybe I take just the first point and I exclude the other. Or maybe I take just the first point and the last point. And I know if I match this and I match this, the software will not make something like this. Will not make something like this. It's obvious that you will make something like this. So I control just the line from 2 points to make it match it in this part. And to build this knowledge in your mind, you need to try that. You need to feel that. You need to practice that. So for that reason, doing a report in this stage is required. It's not optional. You need to practice this. Otherwise, you will. It's useless just to show you without trying. You need to practice that. So here you will see that try to have matching and generate a written report about your work, and this is required. Today I was expecting that each one will try, and I will show you which parameters do you need to use to start tuning process. But I think that few of you have the license now. For that reason, I might have someone who can try this here, or I can do this by myself, but I will not show the solution. I need each one to find this by himself, and it will not take long time. It may take from you maybe 1 day, not more than 1 day. I remember that in our term project last year, it took us at least 1 week to get the match with real PVT data. 1 week. So now we assign the weights here, and before starting tuning, I always advise this. Copy this one here and play with it. If you found that you have destroyed the model or you have worse results, then you delete it and copy it again. Otherwise, you will need to enter the lab experiment giving weights every time, every step. So, yeah, just copying this. Now, the first step, we will try to match DLE data without touching saturation pressure and CCE data. And we found that the only one which has a problem, this one. So we will start by matching this one, gas oil ratio. So we will try to match only this. And we will see if we match this, are we going to make those worse or not? So we will see that now. So gas oil ratio, we already give for this value low volume, low weight. And you can see this here, it's 2. Yeah, I've already said to you, this try to avoid this choice here, the second one, global omega A, omega B. This one can be dangerous because you change omega A and omega B for all components. And in this choice, you will control individual values. For example, for pseudo-components, I will be able to control this. So this one is better. Why? If you read some material about how to tune equation of state, they recommend you to include omega A, omega B for pseudo-components. You are allowed to do that with pure components, but it's dangerous. Try to avoid that. If you are able to get the match without touching pure components, so do it. If you want to try, you are only able to use omega A and omega B for pure component, but that can be dangerous. That can destroy your model. So avoid second choice and deal with others. They use multiple or different techniques. But in our lecture, maybe we use the first or the third one. Before that, yeah, I will go here. There's a note here that you should edit the pseudo-component properties within this range. How I said that to the software. So to do that, just go to regression. Remember that I go back in this step because and I will repeat it here. Or I can delete this and do it here because if I do it here when I copy this, I don't need to repeat that at each time. So just go here, regress, and this button change. From this button, you will be able to give to see the option or available options for your tuning process. So here it's general, here about regression. This one. So here you will see that regression probability range. It's divided for binary interactive coefficients and not binary interactive coefficients. So they deal with this in different way than this. Why? We said this last lecture, maybe someone remember. Why we deal in binary interactive coefficient with different way? Do you remember? Okay. Because binary interactive coefficient can be considered as a tuning parameter. It's related to physics, but it can be considered as a tuning parameter. It means that I can use this number in the way to match the physical progress. So we deal with this number as the tuning parameter, the tuning process with this number, it can be considered as a mathematical problem. You will change that until I get the match. But that's not the case with other properties. You are not allowed to change the critical temperature in a different way or in a very big range. So for that reason, it's acceptable here to say 1.5 and 0.5 for binary interactive coefficient. However, in other properties, you need to take the general advice. So change this number to 1.1 and 0.9. Sometimes, maybe someone can ask, okay, if I make this range wider, it will help me to get the match. Just try that at home. You will find that the more complicated the process will be when you make it wide. So that's the case. So try to change a little bit always with fewer parameters and so on. Here, there's something good also. They give you the choice to exclude the pure components from your tuning. So we don't check the pure components. You will find that here you are able to choose this. But if I press this and this, you will not find those anymore. And we will try that now. We will try that now. So for volume shift, I think it's allowed to change the pure component for volume shift. For DC, DC, AC, that you cannot include that. They are measured in lab. They are already known. So for differently, for this one, you need to uncheck that always. For this one, you may do that, and you may not. One moment. So you see that you cannot choose that here. I repeat now, maybe someone want to see that again. Change, regression, and now we will try to match only GOR without touching anything else. We saw when we show the results, equation of state results with lab, we found this is the only problem that we got. And we saw that from average absolute error. So now we will try to improve this slide, try to match this with lab measurement. And you are always able to get the match. Don't worry about having your data match. You are always able to get the match. But the question, is that correct or not? Is that correct? This is the question. So now we will see, are we able to match this or not? So we will take, and maybe we don't choose volume shift because we want to keep the density matched. We don't want to change this, and we don't want to change binary interactive coefficient because we don't know. Maybe we mismatch our saturation pressure. So we just use those, and we see, are we able to match GOR without destroying other measurement or not? So now to do that, it's just press regress. Here you can specify the number of iterations. So here it's usually 200. You can do that 100. You can choose any number you like. Here it's your iteration step. And here it's the best error you can achieve. If it's like this 0.00, it means that you got the match. However, you are not, I mean, you don't have to wait until you finish 200, the maximum number of iterations. When you find low error, you can just cancel. When you press cancel, the software will take the best error that you could achieve. So, and there's a message to say that it has been cancelled and it will take the best results that you could achieve. So just press OK. And here it shows to you what the values that have been changed to get the match. So you change it this, and ascending factor. You may pay attention on this. It's always the critical temperature. It's always increasing, and this one is always decreasing, and this one it's always increasing. If you match your data and you find that this one increasing until this point and decreasing here, that's wrong. If it's decreasing and this point increasing, that's wrong. And the same here. That can only appear if you make your range wide. But we already solved this. We make the range very small. So even this number is allowed to change by 10% above and below. So it will never be less than this, and it will never be bigger than this. So it's solved. So that's why I said it's dangerous to keep the range 1.5 and 0.5. If you want to do that, do it, but take care in this slide. But now let's see the phase envelope. Oh, we found that our saturation pressure is still matching. So we did not destroy the saturation pressure, but however, we need to go back here to differential and calculate that here, and maybe you saw that it's matching, like without error. But is that true for other things here? So we match that. This one is good to worse. However, we don't know exactly what's the average absolute error here. We can know it if we take the data, and we saw that. So if we take this value, so we found that the absolute average error increased. It was 1.23, and now it's 4. Let's see the other properties. Oil density. You see, you totally destroy the equation of state in terms of oil density. And you can show that from here. If we go oil density, one more. Yeah. One more. I don't think that it. Yeah. Okay. It's still above the. It's above 5%. This one it cannot be accepted. You need to improve this one. So let's see oil viscosity. So you can see that I will show you this one. It should be less than 1%. So we match this. But this one gets worse. This one gets worse also, and this one. So one acceptable, maybe we are acceptable here, but we need to improve those one. However, we did not check CCE, and we will do it now. What about CCE? Is it still below 1%, or it has changed? Let's see that. Oh, CCE, it's. Oh, I need to. Yeah. So CCE. So I think it's still okay for with CCE. So it's 1% here, and it can be accepted. For CCE, I said to you, we already when we reach this step, the second step, we found that for CCE you are able to reproduce it even with below 1%. So here it's acceptable because 1%, exactly 1%. So now we know, we take idea that our model is able to match the data here in this range, to match the saturation pressure here, but here we need to improve that. I will try to fix that here. Okay. We found that also oil gravity changed to 56. So now in my mind, I don't know, but I have different ways to deal with this. So I prefer to copy also this one again and try different ways. So maybe you found this useful with you. When you reach a step and you found different ways to go, don't do that with the same model, because if you do that here, you need to repeat until you reach that point. So at this point, copy the model, and it's free to copy the model, don't worry. So copy the model and try those ways, and compare them with each other. So just before I copy them, I would like to see what I'm gonna do. So we found, according to this one here, we found that oil viscosity needs to be matched, and oil density. Okay, for oil viscosity, we can match that severity without affecting the other results. But the problem now with oil density, we can improve oil density with volume shift, but that may affect those values. And you see, this one is slightly below 5%. It means that small change here may lead to big change here. And we will see that. So, for oil viscosity, just forget about leave it in the last step. I can show you that it's easy to match with critical volume. You know what are you going to change, and that parameter, I mean, can maybe or usually does not affect your results in this side. So for this one, leave it at the last step. And now we will try with oil density, and for that reason I will copy this and you can even match oil density, or just to indicate for what purpose you use this file. So I will say DLE, or we already know it's DLE. So we just type OD oil density. So now we take this model, we try to match oil density for differential. However, I did not compare oil density at this point. I don't know why. No one mentioned this. Okay. So oil density here is 0.619, and how much it was for our lab experiment. Maybe it's better to do it here. So you can see that we have also error. So here we are talking about keep this matched, and for that reason this one we need to keep it matched, and this one. So you found that the error is near. And to me, if I apply the rule, which is using list points, I will try to match only this one, and then I will see, is this improved by matching the density at saturation pressure? Is this improved? Usually it should be yes, be improved. But what are we going to do with those two? So we will see that now. So we are talking about matching oil density at saturation pressure at this point. So now I go to regression. I take Psat density at saturation pressure. And now I just forget about those. And now it may also be different ways at this point. Do I need to check all of them or the last one? It always like this. You think like this. Before, for those ones. Oil density at saturation pressure. So now you have two ways. Either you check all of them or the last one. Using just the first one, it may not be helped. The second one, it may not be helped. Because the rule it says use the heaviest one. The pseudo component, yes, but the heaviest one. If you are not able to use all of them, giving equal chance to be used in the tuning for all of them, it's better than taking the first or the second. However, you are allowed to take the last, the heaviest one in the pseudo component. So here, in this step, I will just try to play with this one, and we will see. We know that the density is affected by volume shift. Someone may come here and play with PC. This is allowed. You are allowed to edit anything in the pseudo component, but you will make the process harder or more difficult. So from here, you found that the best error was very low after just 15 times of iteration. So I could match that point, but how about other things? I can have a general look from the face envelope. So until this point, saturation pressure is still, we can say it's still matching. However, if we want to see it as number, it's changed. It was 2,612, and now it's 4. It's acceptable to be 40 psi above 40 though, but you may need to improve that also. So now we can say that we have a slight problem, not big problem. If this is, for example, 3,000, I can say to you this is not acceptable. But if you are still within a small range, this can be accepted. So, but you always wish to keep this, I mean, improved. So just consider that your saturation pressure now needs to be improved. You need to try more on this. This is regarding saturation pressure. And you see that when you fix the density, the gravity at surface is already fixed. And that's good. On this side, that's good. And now, let's see what happened to DLE. So for oil density, let's start. Let's start from here. This one should be matched. You remember that when we calculate that here, now it's exactly matched. So we match this, and we will see what happened here in this side. Differential calc. So this one should be improved because as I said to you, this point at saturation pressure is the most important point. You always try to pay, attention to this point. But you see, so mistake again. Yeah. So it's okay. Oil density, it's matched now. So, and the question what happened here? We don't worry about oil viscosity because we say we will keep that at the last point. So now we will see what happened here. Oh. So, you see, it was just a slide above, above the 5% in a small range. But when we matched that, we found that we make the process more complicated. So it means that in this stage, it's not easy to deal with this. Okay, we tried the first way. We said that at this step, we copied this here, and we tried with all this, and it doesn't work. So now we should use another way. Now, what about trying to match to match this one, what about trying to match this one with this one, and we include all this with it. So the software will try to match this, and try to keep also this matching. And what happened in this case, or what will happen? So now we can try again. We just ignore this one here. Yeah. Yeah, I named this all. So now we will try to match the density at standard at saturation pressure, density for differential liberation experiment, this one here, and we will try to keep those matches. So this is with low, this is with mid, and we will try. Maybe you are allowed to try something else. You may say, okay, when I tried to match this, I found that there was a big effect here. So you can say, okay, I can, instead of medium weight here, I will get medium weight here and low weight here. But as long as you go out of the recommended guideline, you will make it more complicated. So now, what about those? And for density, I know I need to choose volume shift, and I will choose all of them, and I will choose all these ports. No, this one I keep the data. For this one, I know this one. The same that you deleted. What this one? It's the same that you deleted. Yeah, I know, but I copied this also from this. Oh, so don't worry. Now I will try to match GOR formation volume factor with density, and I choose all of parameters without binary interactive coefficients. Why? Because I used this parameter to match saturation pressure. I don't know if I use it again here, I might destroy or mismatch the pressure there. So I just exclude this. And okay, now it says that the error is 2, 1. So once you are below than 1, you can just cancel. It means that you are within the range. And you may note that the process is easier now because you have a lot of points, and you will change those parameters to improve the equation state at those points. So the process, when you have more points, the process will be slower and more complicated. And if you note that this number is constant, it means that the error at each time step is not, is not changing. So you may press cancel, but we saw that this number is still changing. So it means that there's improvement, but it's slow improvement. So I don't want you to explode. Wait a moment. I will cancel that. Don't worry. So this is acceptable to take that percent of error. But now this this time we mismatch the saturation pressure. But how about the data that I tried to match? Are they okay or not? So, and I can say to you, this is the simplest model in our, I mean, we take the simplest PVT data. You don't know the type of your fluid data. I mean, usually it's more complicated than this. So, now, let's see. Okay. So, you see, saturation pressure, it's totally off. It's not acceptable to be like this. So it's not acceptable to be like this. This one, we will compare it now and see. So this one, still okay, because it's already included in our matching. What about CCE? Maybe we... Okay. So for CCE, it is still okay. But, no, sorry. It's still not okay. So it should be below 1% for CCE. CCE, it's always low, but it should be around 1% or below. Because here you are near to 2%. But if we go to this one, differential oil density, so in this case, when we include all the data, I mean all density, all differential evaluation data, CCE data, it needs to be improved. Here it's okay. For GOR it's okay. Here it's nice, good, and here it's good. So, but is this model good for you? What do you think? CCE, but it's slight above 1%. It's not that. We have one problem here. Yeah, our problem is saturation pressure. It cannot be acceptable to be far from saturation pressure by more than 50%. Even 50%, you need to improve that. So, at this step, it means that we need to go back. We try again. So, now I will just delete this from here and copy it again. Make sure that I am in the range. Okay. So now I will change the way. At the beginning, the first step, we try to match this only gas oil ratio because all results were okay except this. So I tried this, it didn't work. I tried this with other things, it didn't work. So now I will try to include saturation pressure in the same way. And I have also to include CCE because I found that it gets worse. So I can say to you that at this step, oh, okay. I need to check all of them. And okay, the weights are high, medium, low, medium, low, low. Mm. Oh, yeah. This is good choice. This one. If you don't control the range, you remember that we make a range which is 0.9 to 1.1. It means 10% plus or minus. But if I make this range, for example, like this, which means 50% plus or minus, that is big range. In the software, there's a good choice, which you can use this way, use big range, but the software will control that way. It will limit the change in the movement with properties compared to each other. I said to you, the critical volume should be, the critical temperature should be decreasing. And if I have big range like this, the critical temperature for the first pseudo-component can be less than, or it can be not in the suitable way. So by making this a choice, you will preserve that in your model. So you are recommended to use this. And don't use something which you don't understand. Think about it, see what does it mean, and use it. Yeah. So in this case, in my case, I don't need to use it because my range is small. However, if I could not reach the match with this range, I can increase the range to this one here, but I have to check this choice. I feel the things, it's crowded here. A lot of information, but I don't know, but just you will find that in the report, and I hope that each one will, have, each one will try that at home or anywhere you like, but just try that. So in my case, I don't need to check this, and okay, since this time I'm trying to keep the saturation pressure matched, I will include binary interactive coefficient. By the way, for binary interactive coefficient, we have three choices. Either you apply this for the last pseudo component, and this is nice here, because I said to you here, it's okay to choose the last one or all of them. They give you this choice here. last pseudo-component only, or all pseudo-components with the same value. And this is also recommendation. If you use more than one pseudo-component, I mean you have two choices. Either you try the last one, only the last one, or all of the pseudo-component and prefer to be with the same value or near to each other. So we are allowed to choose either this or this. I will choose this because three pseudo-components, all of those, will help me more to get the match. So this is, if I could reach the match with only the last one, it's better. The less parameters you change, or if your change is less, I mean it's better to your equation of state. Once you found yourself you are changing a lot of things, then you know that you will destroy your equation of state. But in this case, I think it's not possible to achieve matching with only last pseudo component. So that's why I choose all pseudo components. And now we will see how can I achieve matching. And you will see that each, you see 5 seconds, and I'm just done with the first iteration. So it takes longer time, and the process is more complicated. And even if you see low percentage here, you cannot know exactly how your model is doing, because when you calculate average absolute error, you will find exactly the right percentage for each point. Why? Because we include GOR, beta O with a lot of points, and saturation pressure is 1 point and can be mismatched. So this number here may not give you indication about the percentage of error, because if you have only saturation pressure and match it, you will not see that from there. You will see a nice percentage there, but if you go and check your saturation pressure, you might find it totally off or far away from the lab measurement.
And why if we don't start from this last point and try to match all the properties?
The general rule, it says start with fewer data. So you always wish to make a slight change, not big change. And going from the first step to change everything to get the match, can be danger. And we will see, even with doing this, you will not able to get the match from the first step. You will need to try that more and more. So, you can just stop the process anytime you like. Just press cancel, and if you think the software is not able to improve that, just press cancel. But here we found that it's still improving, because the last step is the same as error. It goes to the right direction. You have the push. Yeah. We use binary definition to match saturation pressure. We try to match a lot of things at the same time. We use, yeah, we check because we match this. It will change, it will be changed. And for that reason, we know that if we change those properties, the saturation pressure will be affected at keep that matched at the same time, we include binary reaction coefficients. So we change those, the saturation pressure is changing, and we match it again by this value. So you are controlling process computation. You try to match something. Yeah, yeah. Because as I said to you, you change those values to match all data that you have, but your saturation pressure will be changed. So you after changing those to match your lab data, then your saturation pressure is changed, and then you match that by this. This is the way of thinking in this system. So we just press cancel. I don't know, but I think that if we keep it, it will not improve so much. You find that it's only one number degrees. So okay. So we include saturation pressure, and saturation pressure got the highest weight. So in this complicated process, you will find that you could keep the saturation pressure matching. Why? Because we give the highest weight for saturation pressure. But how is our model with other lab data? And now we will compare that here. So for density, we can see it's still okay. So let's. So saturation pressure is above the lab mid. So it should be 20 and it's 39 or 40. You can see say 40. So, but for density, we can also include BSAT here. So it's still below 1%, even in saturation pressure. This is for saturation pressure. So with BSAT, we are okay. Now let's see CCE and DLE. So it's also okay with CCE. So until this step was okay. First one, the second one was okay, and now we will see DLE. So oil density should be good because we already matched the oil density at saturation pressure. So it's still below 1%, 5%. So you found that we are still at the same point. After even matching, we have this is not good. And for oil viscosity, I always say forget about it. Take it as good. So at this point, I will not retry this way. This is your homework. You will try, you need to try. If I know this is not useful, I will not ask you to do it. This is very useful for you. This will help you to work in your term project. And if you know it will take too long time, just say this is the best result that I got. Even if you could not achieve if you could not achieve a value below 5% and you found this is very boring, just say, okay, this is what I can achieve. You will not lose any marks, but you have to handle the report, even with one page. Just show that you tried something. Okay, I will not repeat this. I will just assume that we could match this, and everything is matched except oil viscosity because we have not tried with this. We will see now. If I match all data and I have only this problem, this is easy. For this one, we say for oil viscosity we match this by, alone, separately. So we cancel from here and we assume that we match everything there, and now we go to this oil viscosity. For oil viscosity, you have to try with different kinds of models. Oil viscosity is described, I think, as far as I remember, in different models. It's not related to equation state. However, it takes maybe some values from equation state. I'm not sure about this. You have to read about it. However, in the software, you are allowed to use different models, and which one you are, you're supposed to choose when you compare this with lab results. If this one gave me the lowest percent of error, then this is the most suitable one. So I will not change this. I'll just take this, try to match viscosity, and I want to see at the same time. If I match viscosity, is this changing? Is this changing? Because it means if I match this and those one change, it means that I might match this and destroy all of this here. And then I make the process more complicated. So usually, critical volume, which is used to match viscosity, oil viscosity, is not used in our calculation equation system. So that's why, if we match this, we should not see big change here. And we will see that. We will try to match this, and we will copy the equation state measurement and see, is this affected? Is this affected? And this is the last point here for today. So I will copy this, and I name it oil viscosity. And I will compare. If I match this, what's the difference between this and this? I should not see big effect. So I did not change those. I take. You see that this is good thing. The software gives you only critical volume as a choice. Here, the software it doesn't show to you other problems. This is good in this software, but in PVTI, you will not see this. You are allowed to check anything. So you will be happy check other things, and this is may also destroy your model. For viscosity, always choose critical volume. For density, volume shift. For viscosity, critical volume. Yeah, I'm not sure about this choice. However, we will see. We will try now. The first step, try to change the critical volume for all pseudo components. If it doesn't work, change the model. If it doesn't work, change the model. If you have tried all the models, then you might include this choice. For example, allow user oil coefficients, which will use a coefficient for all components. And it will not change the critical volume for pure component, but it will change coefficient. And that coefficient will be used to improve your results. So you are allowed to use this. Don't worry about it. So now let's start by this. And we found that it's still high, but we will need to compare that. We don't know. We will. I will just compare that, and I will see. I can see from my face envelope that saturation pressure is not effective. I can compare my current case with the previous case with selecting those, and I see there's no change here. It means that my changing the critical volume does not affect the previous model. So if we are talking about density, it's still also the same. Let's go to differential. Maybe we use this plot here. Oil, viscosity. So we tried to match this. It's near, but we don't know the average absolute error. So let's take those values. So no improvement. I think it's, or I cancelled the process. I don't know what happened. I will repeat that. Yeah. It seems that there is no improvement in terms of oil viscosity. So it's still the same. It means that you need to try with another model. I don't know, but maybe this model is more effective. I will try it, and yeah. Okay, it's reduced under 15, so it's lower than before, and we will compare that to see. Uh, this model, Little Kennedy. I don't know if he's the same president of America. Yeah. We have names, but everything is mixed here. Yeah, we go again. So, with this model, we could achieve. Mhm. This is the person. No, it was 10% or 11. Now it's 1%. So we could match viscosity. But let's compare the other things. Are they affected or not? So density. So density, it's already below 1%, and we will see now. You see. Oil. So, at the end, our conclusion, when I match the density, the viscosity, I might destroy other lab experiments. Why? In the first model, you remember, in the first model, there was no effect here. But when we changed the model, there was effect. Can someone know why? Okay. Do you know why here, when we try this model, the other properties were changed? Do you have idea? Okay. Because here in this model, we changed the critical volume for all components. If you do that for only the pseudo-components, you will not destroy your model as you see here in this model. So you are between two things, some of them which is bad, and the other, I mean, it can be bad and good in different ways. If I use this model, or any type of model which use the critical volume for all pure components, I can get the match, but I will need to rematch all the process that I did or I've done. But if I use the first model, I can improve the viscosity, but maybe that model is not enough. So now you understand what's your duty. Okay, that's it for today. Thank you.